Okay, IBAASL2 kids. We've reached the end of Chapter 5. The next assessment is going to be over 5.4 and 5.5, which I'm calling Derivative Applications. So, the first thing we're going to talk about is the connection to a graph. For a while now, we've been talking about how if you take the first derivative and then you set it equal to 0, that you can solve for turning points. That solving might involve, factoring quadratics or factoring common monomials, usually factoring or just straight up solving in our usual solving ways. After that, we kind of looked at these things I call zone tests, where you put the turning points out on a number line, and then you pick values in between the turning points and outside of them and such in the different zones. And if it switches from like increasing to decreasing, that would be a local maximum. And if it switches from decreasing to increasing, that's a local minimum. It also tells you where the original graph is going uphill and downhill in terms of the slope of a tangent. Remember we did talk a little bit about global maximums and global minimums, because sometimes if they restrict the domain, you have to check the endpoints in the original equation to see if your local mins and maxes are bigger or smaller than the y values of your intervals, your x intervals, that your domain. Then we started talking about the second derivative. Second derivative is just derivative of a derivative. When you set that equal to 0, one of the main uses of a second derivative is you can actually not do the first derivative zone test and just plug in your stationary points or turning points from your first derivative, and then if it's concave down or concave up, it's a local minimum. If it's concave down, it's a local maximum. I've already been talking about that word concave. Yeah, second derivative tells you about the concavity of the original function. When you set the second derivative equal to 0, you find the inflection points, possible inflection points, because sometimes there's those faker inflection points in there. The way you tell if they're inflection points or not is you do a concavity zone test. So you put your inflection points out on a number line, then you pick numbers from the different zones. You test them in the second derivative, and then, if it switches from positive to negative, or, up to down or down to up, those are true inflection points. If they don't switch, if they go from up to up or down to down, this is what the book is calling horizontal points of inflection. This means that there's no change in concavity, and it's a stationary point but not a turning point. If you can't picture what that looks like, try this on for size. If you're coming down and then it flattens out and then it keeps going down like this. This point right here, it doesn't change concavity because it's concave up here and... Wait, no, that would change concavity. That's a bad example, Jolly. We had one where it doesn't change. So just trust the zone test. That, if it goes from up to up or down to down, it's a horizontal point of inflection. Now, we threw some graphs at you guys, original f of x's, and then asked you guys to sketch the first derivative and second derivative on those original graphs. Remember to get the first derivative, you really just look at where the turning points are. Those turning points are where the first derivative should cross the x-axis, because those are zeros in the first derivative. Whenever the original graph is going uphill, that's where the first derivative should be above the x-axis. Anytime the original graph is going downhill, that's where it should be below the x-axis. You should also be ready to take the original function and find the second derivative. There's two ways to do this. You could just look at the first derivative and then do the same process again of where are the turning points on the first derivative, because those will be the zeros of the second derivative. Or you could just look at the original graph and look at where the inflection points are. Remember, inflection points are where the concavity changes from either up to down or down to up. Those should be the zeros where it crosses the x-axis of your second derivative. And then anytime the original graph is concave down, your second derivative should be below the x-axis. Anytime it's concave up, it should be above the x-axis. Now, a lot of people have been like, you know, Jolly, what was this going to look like on a test? Are we actually going to have to sketch these things? How exact do I have to be? I'm thinking that when it comes to a test, we might give you one of these guys, either the derivative or the second derivative, and then ask you some questions about the original. So we might ask you where the original is increasing or decreasing in terms of intervals. We might ask you where it's concave up or down in terms of intervals. We might ask you where the turning points are or where the inflection points are. Optimization. There's really no good way to tell you how to study. Well, no, I mean, do all the homework problems and review problems, do everything you can get your hands on for optimization, because it's really kind of a crapshoot about what you're going to see in terms of an assessment or an IB exam. So far, we've done folding box problems, we've done rectangular pen problems, we've done profit problems, which are revenues minus cost, and then we've done some basic geometry ones where you guys are finding like either perimeter or area of like rectangles and squares. I think those are the shapes that came up. I don't even think we did a triangle. With all of these, this is kind of the process you guys should be going through. You try to write an equation, or hopefully they give you the equation, because sometimes this part, writing the equation, is like the hardest part. Then they usually involve taking a derivative, finding the turning points by setting the derivative equal to 0, and then determining if they're local maxes or mins, and you can do that with the second derivative or first derivative zone test. The last subject we tackled, kinematics, the study of motion, I think. Remember that if you have like a they usually give you an original function that's like a displacement function, and then the first derivative of that is the velocity equation, and then the second derivative of the original is the acceleration equation. There might be some questions about like where it's speeding up or slowing down. Remember that if you find the zeros from the acceleration equation and the velocity equation, you can do a giant zone test where you plug in pick points from around sorry, I'm stumbling. You find the zeros from the velocity equation and the acceleration equation, and you do a big zone test, pick points from in between the zones from those zeros from acceleration and velocity, and then put them into both of these. It's like a double zone test, acceleration and velocity. If the signs agree, like plus plus or minus minus, that means it's speeding up the particle. It's usually a particle problem. If they don't agree, that means that it's slowing down. Okay, you guys, I think that's about it for now.